So today we're going to have a look at non-uniform motion. So we're now considering situations when velocity is not consistent over time. And these situations occur quite often, including scenarios like projectile motion. So as you can see down the bottom here, we've got a projectile path. So this could be any object thrown or launched along this path. At the start, we've got the velocity vector going up like this. At any other time though, our velocity vector, so we'll take that second dot, is going at a tangent to the curve. On the way down, it's going like this. Well, not quite, but you get the point. So it's not constant, and that's the point of these this whole video: non-constant velocities. So we're interested in a few things about these types of curves. The first one is the velocity vector. So if we've got an object moving and we're calling that p of x, and the x component is changing with time, and the y component is changing with time, the velocity vector, so how fast it's moving, is the derivative of each of those parts. So the x component of the velocity vector is the derivative of the x, and the y component is the derivative of the y. Now that's for the velocity vector. If we're talking about speed, it's the same as what we've been doing before in vectors and also with the constant velocity. It's just the length of that velocity vector, meaning we just square each part and take the square root of the sum. Okay, so that's consistent with what we've seen. This might be a little bit new, but hopefully nothing too shocking. All right, so it also appears that we're also interested in the direction of the motion, and it appears that that is always tangential to the curve. So we drew that in the first slide. It was tangent at all times, and we can prove that. So the gradient of the velocity vector any time is y dash t over x dash t. So if we substitute in our values for that, it's dy by dt for the top, the numerator, and the denominator is dx by dt. Now, we know if we divide by a fraction, it's the same as multiplying by the inverse. All right, so dy by dt is the numerator. Instead of dividing by dx by dt, we can multiply by the inverse, so dt by dx. All right, now what we know is by the chain rule, we can cancel these out and we're left with dy by dx, and that's by the chain rule. So basically what this shows is we were looking at the gradient of the velocity vector, and we found it was the same as dy by dx, so the velocity vector is tangential to the curve, all right, which is what we guessed, but this is a quick little proof to show that. So let's have a look at an example now. So we've got a couple of equations, x of t and y of t. T is always greater than 0 seconds, and it represents the flight of an arrow fired by an archer sitting in a tree. Y equals 0, so the height is ground level, and the distance we're going to use are meters. So there's a bit of information there. So let's have a look at part A. How high in the tree was the archer when he fired the arrow? All right. So when the archer fired the arrow, that's going to occur at t equals 0 seconds. And the height is dependent on the y, because we know, just like a standard Cartesian graph, y is a vertical, x is a horizontal. So we're interested in the vertical. So at y of 0, that's going to give us our height. We're going to get 7 plus 28 times 0 is 0. Take 4.9 times 0 is 0, so it's going to equal 7. All right. Therefore, how high was the tree and the archer when the arrow was fired? So you write a little sentence. So when arrow was fired, the archer was 7 meters, and we like to use 7 meters. We use the language like high. Sometimes you could write above ground level, but I just like to use the language they use in the question. All right, so that's part A. So next, so that was part A. Next, we'll have a look at part B. So what was the total time of flight? So we know our arrow is flying from 7 meters high in the tree. They're shooting the arrow and it's hitting the ground some height later. The height we're interested in later is when it hits the ground, which will happen at y equals 0. Okay, so if we want y equals 0, we've got 0 equals, and our y is this one here. So 7 plus 28t take 4.9t squared. All right, so we could use a few things. We could graph this. We could use the quadratic formula. I'm just going to use the calculator. So we're going to substitute these in the calculator and solve it for a polynomial degree 2. All right, so I've just put in the values there. So the thing in front of x squared was actually negative 4.9, but it doesn't matter. I've flipped all the signs. So about negative 4.9, let's put that in. In front of the y, the t was 28, and in front of the constant was just 7. So if we put all of those values in, we get two numbers, 5.954 and negative 0.23. But the initial condition said t has to be greater than or equal to 0. So therefore, t equals 5.9. Oops, what was it? 54 or just 4? 954 seconds. All right, so that's part B done as well. All right, so now part C. We're interested in how far the arrow flew horizontally. So that's going to go from, it started at t equals 0. T equals 0 was the start, and it went to t equals 5.954. So if we substitute 0, x of 0 here, so x of 0 equals, so we get 2 plus 0, so it's just going to be 2. So that's the starting position, 2. And then we get x of 5.954 equals, we're going to have to substitute that into our calculator for t. So let's do that now. So after 5.954 seconds, it flew 151 meters. So what we get is, therefore, it started at 2, finished at 151. So therefore, 151 minus 2 equals 149. So the arrow flew 149 meters from the tree to the ground. All right, excellent. Let's have a look at another couple of parts of this. All right, so part D, let's have a look. What was the maximum height reached by the arrow? Now, the maximum height reached by the arrow, if we go back to our picture, is going to happen when we're here on the top of the parabola. So at the top, we know the tangential speed is horizontal, and hence y dash of t is going to equal 0. We get that horizontal line. The slope is 0. All right, so going back here, we know that y dash of t equals 0. So y dash of t is going to be equal to the 7. Just when we differentiate, that goes away. It's going to become 28 take 9.8 t equals 0. All right. Therefore, we rearrange this. Therefore, t equals negative 28 divided by negative 9.8. All right. Again, we put that in our calculator, and it equals 2.857 seconds. Okay. Back to the original question though. So it said, what is the maximum height? So now we've got to take this and we've got to put it back into the equation for y. So y of 2.857 equals, put it in there, we get 7 plus 28 times by 2.857. take 4.9 times by 2.857 all squared. Again, we're going to put that straight into our calculator, and we get it equals approximately 47.0 meters approximately. All right, cool. So that's the height of the arrow reached. Let's have a look at the next one now. So let's find the velocity vector for the arrow. So we remember that, so we're doing part E. The velocity vector for the arrow was equal to x dash of t, y dash of t. So basically we just have to derive with respect to t both of these things. So we take the first one, it's going to be 2 goes away, 25t becomes 25. And the second one is going to become 7 goes away, 28t becomes 28. And negative 4.9t squared becomes negative 9.8t. All right, and that's it for part E. So part F, we want to find the arrow speed initially. So again, we're going to use this. So v at 0 is going to be equal to 25, and we put 0 in the bottom one, 28. So that's the vector speed. Sorry, the vector velocity. We want to find this speed as well. The other one we want to do is find it after 4 seconds. So we want to substitute 4 in here as well. So v of 4. So this is I. This is 2. V of 4 equals, again, that x component is still 25. The y component becomes 28. Take 9.8 times 4. All right, let's just put that in our calculator. All right, so that's negative 11.2. And because we've been asked for the speed, we just have to take the square root of each of these components squared, 25 squared plus 28 squared. And that's for the speed. We'll call that v equals. And we'll do that for both sides. So if we substitute those in, we get 37.5 meters per second at the start. And at the end, we get 27.4 meters per second. All right. So, yep, that's the answer to part F. So, G, at what angle was the arrow fired? All right. So what we want to do is we want to find the velocity vector at t equals 0. So the velocity vector at t equals 0 was equal to, if we go back, have a look, 25 and 28. 25 and 28. So what this means is the x component was positive 25, the y component was positive 28, and this was the total velocity here. And we're interested in the angle. So we have the opposite and the adjacent. So what we're interested in is when you have the opposite and the adjacent, you're interested in tan. So tan of theta equals opposite 28 divided by adjacent 25, and hence angle theta equals the inverse tan of 28 over 25. And we just put that into our calculator. We get 48.2 degrees. What you want to write is a little sentence saying something like arrow fired 48.2 degrees. You can see it's going upwards, so we call that above horizontal. Above horizontal. So there you have it. And lastly, what angle did the arrow strike the ground? So then we've got to go back and we've got to realize that it was like 5.954 seconds. Put that in, work out our velocity vector, and do the same thing as here. So have a go at that. Otherwise, yeah, that's it. So we'll have a go at a couple of these now.